Welcome to our guide on working with panel data. This presentation provides a step-by-step approach to understanding its structure, visualization, and analysis. We will cover the entire workflow from model selection and estimation to running essential diagnostic tests, with a focus on practical implementation in EViews. Panel data offers significant advantages, primarily by increasing the number of observations and allowing us to control for unobserved heterogeneity, which are crucial for robust econometric analysis. This slide introduces the concept of the data rectangle, which helps in capturing both heterogeneity and dynamics in economic data. Real-world economic data is rarely one-dimensional, and panel data is designed to track multiple entities, such as firms or countries, over time. As illustrated, a single entity over time represents a time series, while many entities at a single time period represent cross-sectional data. Panel data combines these, forming a grid with time, t, on the vertical axis and entities, n, on the horizontal axis. We then distinguish between two main types of panel data. A balanced panel means that every cross-section has data for every time period, implying there are no missing observations, or holes, in the data rectangle. Conversely, an unbalanced panel refers to situations where some cross-sections are missing data for certain periods. It's important to note that statistical software like EViews can handle both balanced and unbalanced panel data, although the structuring process may differ slightly for each. Welcome to our overview of the panel analysis workflow. It starts with data entry, where you import your data, whether it's stacked or unstacked. The most crucial step is structuring, where you must explicitly define the ID and date series. This is a critical warning. EViews treats your data as unstructured until you explicitly define these panel identifiers. After structuring, you move to visualization to examine your data's range, denoted by n times t. Next is estimation, where you select your model, such as pooled OLS, fixed effects, FE, or random effects, RE. Finally, you perform diagnostics, which includes tests like the Houseman test, redundant FE tests, and unit root tests. Don't forget that crucial structuring step. This decision map guides us through choosing the appropriate estimator for panel data analysis. We start with the overall concept of panel data analysis. The simplest, but often risky, approach is pooled OLS, which assumes homogeneity and ignores individual differences, often leading to incorrect inferences. A more robust method is the fixed effects, or FE model. This model focuses on within-group variation and effectively controls for any unobserved characteristics that do not change over time for each individual unit. Then we have the random effects, or RE model. This model assumes that the individual effects are random and, critically, uncorrelated with the explanatory variables. If this assumption holds true, the RE model is more efficient than FE. To formally decide between fixed effects and random effects, we use the Houseman test. The null hypothesis, or HO, of the Houseman test is that random effects are consistent and efficient. The alternative hypothesis, or H1, states that random effects are inconsistent, implying fixed effects should be used. The decision rule is straightforward. If the p-value from the Houseman test is less than 0.05, we reject HO and, consequently, choose the fixed effects model. Alert! Fixed effects estimation consumes n degrees of freedom because it technically accounts for n intercepts. If n is large and t is small, this is costly. First, we have strict exogeneity. This is a strong assumption, stating that the error term, UIT, is uncorrelated with past, present, and future values of the explanatory variables. Second is homoscedasticity, which means the variance of the error term is constant across all individuals and time periods. Third is no cross-sectional dependence. This assumes the errors for one unit, say Germany, are not correlated with the errors for another unit, like France. This is often violated in macro panels. Fourth, for panels with a long time dimension, large T, we need stationarity. The variables should not have unit roots, which could lead to spurious regression results. If heteroscedasticity or certain forms of cross-sectional dependence are suspected, robust errors are necessary. EViews offers options to compute these robust standard errors. Specifically, you can select white cross-section, which clusters errors by period, or white period, which clusters errors by cross-section, to address these issues. This slide explains how to interpret coefficients in panel data models, specifically distinguishing between the within estimator, fixed effects, and the between estimator. The within estimator, also known as the fixed effects model, examines how a change in the explanatory variable x over time affects the dependent variable y within the same entity. In contrast, the between estimator focuses on how differences in average x across various entities affect average y. A crucial point for fixed effects models is that time-invariant variables, such as geography or gender, cannot be estimated. These variables drop out of the model because their change over time, denoted as delta x, is always 0, meaning they cannot explain variation over time. Structuring your data is the foundational step in EViews. You begin by opening the Work File Structure dialog. First, you must set the work file structure type to Dated Panel. This tells EViews you are working with panel data. Next, you must specify the panel identifier series. In the cross-section ID box, you enter the name of the variable that uniquely identifies each entity, like ISO code for countries. Finally, in the Date Series box, you enter the name of the variable that identifies the time period, such as YR for the year. EViews can often auto-detect the frequency, like annual, if the date series is formatted correctly. If your Excel file has a column named Country ID and another named Year, you would enter Country ID into the cross-section ID box and Year into the Date Series box. After clicking OK, EViews will understand the panel structure of your data. After defining the structure, it's crucial to verify that EViews has understood it correctly. Once you've structured the work file, the top of the window will display the range and sample. This is your verification step. The range tells you the total canvas of your data. It shows the start and end dates, the number of cross-sections, n, and the total number of potential observations, n times t. The sample indicates the subset of the data that is currently active for analysis. By default, it's usually the same as the range, but you can change it to analyze a specific subperiod or a subset of individuals. For example, if the range shows 1950-2000 times 208, it means your panel data runs from the year 1950 to 2000, covers 208 cross-sectional units, and has a potential of 10,208 observations. Seeing this confirms that EViews has correctly identified your panel's dimensions. With the data correctly structured and verified, we are now ready to estimate our models. This slide shows the Equation Estimation dialog in EViews, which is where you configure your panel data models. Under the Panel Options tab, you'll find crucial settings. First, in the Effects Specification section, you select your desired model. Here, the cross-section dropdown allows you to choose between fixed or random effects, which is central to our discussion on model selection. Below that, the CoF covariance section allows you to choose the type of covariance matrix. For instance, you might select white period or white cross-section to account for potential heteroscedasticity or cross-sectional dependence, making your standard errors robust. Further down, under Weights, you can select specific weighting schemes like cross-section weights, GLS, for more efficient estimation under certain conditions. On the right side of the slide, we have a quick cheat sheet for EViews commands, showing how to execute pooled OLS with LS-YCX, fixed effects with LS-CX equals F, and random effects with LS-CX equals R directly in the EViews command line. Why categorize? Use stats by classification to see if means differ between groups. If means are identical, a pooled model might suffice. Large differences suggest fixed effects. In a fixed effects model, the C coefficient represents the average intercept across all cross-sections. Specific effects are deviations from this C. This slide walks us through reading the output from a panel least squares regression in EViews, specifically for a fixed effects model. First, focus on the coefficient column, which shows the estimated marginal impact of each variable. For instance, the coefficient for val of 1.305214 means that a 1-unit increase in val leads to a 1.305214 unit increase in the dependent variable, INV, holding other factors constant. Next, under effects specification, you'll see cross-section fixed, dummy variables, which confirms that a separate intercept was estimated for each cross-section, effectively controlling for individual specific time-invariant effects. Finally, at the bottom, we have key diagnostic statistics. The F statistic of 112.5432 and its associated probability of 0.000000 indicate the overall statistical significance of the model. Additionally, this section mentions the redundant FE test, which you would run from view fixed/random effects testing redundant fixed effects. If the probability associated with this test is less than 0.05, it implies that pooling the data using pooled OLS would be a mistake, and the fixed effects are indeed necessary. This slide presents a crucial diagnostic step in panel data analysis, the Hausman test. The primary purpose of the Hausman test is to help us decide between using a random effects, or RE, model or a fixed effects, FE, model. The random effects model is generally more efficient, meaning it produces estimates with smaller standard errors. However, this efficiency comes with a strict assumption that the unobserved individual effects are uncorrelated with the regressors. The Hausman test is specifically designed to check this assumption. The output table displays the results for a correlated random effects Hausman test. We are particularly interested in the row labeled cross-section random. For this specific test, we observe a chi-square statistic of 12.3456 with 2 degrees of freedom, and most importantly, a probability, p-value, of 0.0021. The decision rule for the Hausman test is straightforward. If the p-value is less than our chosen significance level, typically 0.05, we reject the null hypothesis. In this case, since 0.0021 is less than 0.05, we reject the null hypothesis. This rejection implies that the individual effects are indeed correlated with our regressors. Therefore, to ensure consistent estimates, we must reject the random effects model and proceed with the fixed effects model. Stationarity is a critical assumption for time series data, and it extends to panel data, especially when the time dimension is large. This is often called a long panel. If your variables are non-stationary, meaning they have a unit root, you run the risk of spurious regression, where you find a statistically significant relationship that is actually meaningless. Panel unit root tests, such as the Levin, Lin, and Shu, or the Im, Pesaran, and Shin tests, are used to check for this stationarity. The null hypothesis for these tests is that the series has a unit root. In other words, it is non-stationary. Therefore, a small p-value allows you to reject this null hypothesis and conclude that the series is indeed stationary. For instance, if you are analyzing monthly stock prices for 50 firms over 20 years, your time dimension is large, specifically 240 months. You would need to test each series, such as stock price or trading volume, for unit roots. If a series is found to be non-stationary, you would typically analyze its first difference instead of its level to achieve stationarity. To recap the key steps in panel data analysis, first, structure first. Always define your cross-section ID and date ID correctly. This is the absolute foundation. Second, visualize. After structuring, check the range, denoted by n times t, to ensure your panel dimensions are recognized correctly. Third, estimate. Generally, use fixed effects to control for unobserved individual specific factors that don't change over time. Finally, verify. Employ the Hausman test